Hello. Today I have with me a tornado. And the question is, are tornadoes more common than they used to be, especially here in the United States? Hopefully by the end of this section we'll have an answer to that. And to do that we need to analyze some data. And to analyze some data, we need a good criteria of finding a good model. And we've talked a little bit about that in the past, but now we want to become more precise in how we tackle that. So let's talk a little bit about something called least squares regression. So how are we going to tackle this? Well, consider a model, f of x, for some data that we'll just call x sub I, y sub I, where I ranges from 1 to n. So we have n data points, and we're trying to find some function that will model those data points. And there's 3 possible criteria, more than 3 actually, but 3 that we'll talk about, of finding the best model. And when I mean best, what we're trying to do is figure out a way to analyze the data as a whole, not just look at, say, percent error or, after the fact analyze it, but to actually find the model in the first place that actually is the best. So the first criteria is to minimize what we'll call WCE, or in other words, worst case error. And WCE is just the maximum as I ranges over 1 to n of the absolute error, yi minus f of xi. So if you think about if the data point is at xy and I have f of x as my model, then f of xi is my prediction. This is my actual. And so the difference between those two is a measure of how good my model is, and I would like that to be 0 or close as much as possible. And depending on your situation, having a bunch of error close to 0 and then one data point that's really far off may be okay, or that may be the worst thing that you would want for your model. And so if that's the case, then you want to minimize the worst possible case error. And so that's what criteria number 1 does for us. On the other hand, maybe I don't worry so much about one data point. I want all of them to be a good fit. In that case, we want to minimize SAE, which is also called the sum of the absolute error. And SAE is similar to WCE, but I'm just summing instead of finding the largest. Number 3 criteria is similar, but instead of finding the sum of the absolute error, I'm finding the sum of the squared error, which might seem a little odd at first. So here's the formula. So I have the sum of yi minus f of xi, that difference squared, and I'm summing over all those from 1 to n. So what do these two have in common? In both cases, that difference between the prediction and the actual could be positive or negative. And if I'm going to add those up, I can't be adding positive negatives or they'll cancel each other out, which will be misleading. So I need to make them all positive. Taking an absolute value or a squaring will both accomplish the same thing. Seems like the absolute value might actually be a more logical choice. But if you think about where we're headed, the goal on all of these is to minimize this quantity. Well, if you remember back to calculus class, if I'm going to minimize something, I need a differentiable function, something that I can find derivatives of so I can apply the properties of calculus. And as you may recall, the absolute value function is not differentiable, but the squared function is. And so it turns out it will be easier to apply calculus to SSE than to SAE. And so that's why historically this form of error analysis has been the choice. And it's also why we have our name, least squares regression, because we're taking all the squares and then making them as small as possible. So in particular, we're going to look at linear regression. And we're just looking at the basics today. And so we're going to assume that the data is approximately linear. And so we're going to let our model be of the form mx plus b. And our goal is find m and b. Now, in the past, we've done this with trial and error, or maybe we've looked at percent error, but now we have a criteria, and because of the rules of calculus, we're going to find m and b to minimize SSE, which I'll give a name of just E, make it a little bit easier to write. And E is just the sum. I'm not going to keep writing the ones and the ends. So E is just yi minus, and now that we know the function, this is mxi plus b. And we're squaring that entire difference. So we have a function. Notice it's a multivariable function, so this is going to require calculus of the multivariable variety. But it's okay because we can do that. It still involves derivatives. So the first step then is to find the partial of E with respect to M and the partial of E with respect to B, are two variables. So keep in mind here, X is actually not the variable because we have values for X. Remember, X's and Y's are known, but the M and the B are the unknown variables in this problem. So that's why we're taking derivatives with respect to those variables. So how about the partial of E with respect to M? So we have the summation. We can move the derivative inside that summation. I can bring down the 2. So I have yi minus mxi minus b. And then by the chain rule, I can multiply by a minus xi. Likewise, the partial of E with respect to B is the sum, once again, 2yi minus mxi minus b. And the derivative of this interior quantity with respect to b is minus 1. And we want to set both of those equal to 0. And hopefully we'll be able to get equations that I can solve for m and b, which we'll leave some of this for the exercise so you can try it on your own. But notice that is in fact what we get, is if we clean this up, set this equal to 0 and clean up a little bit, we get the sum of 2 yi xi, right? So if I bring that over to the other side, and then equals the sum of 2mxi squared plus the sum of 2bxi. So that first equation set equal to 0 gives us something of this form. In fact, we can even cancel the 2 if you prefer. And we still have something where we can pull out the constants. We can pull out the m. So we have the sum of yi xi equals m, sum of xi squared, plus b, the sum of xi. We can do this similar thing for the partial of E with respect to B. So likewise, partial of E with respect to B equal to 0 gives us the following formula. I'll let you do the algebra and check my work. The sum of the yi's equals m times the sum of the xi's plus b times n. And the good news is we have two equations, two unknowns. Here's an m, here's an m, here's a b, here's a b. And so these are two linear equations, in fact, because the m's and the b's don't have any powers or anything. So two linear equations and two unknowns. So solve for m and b. Again, that's an exercise. It's a nice algebra problem, but in case you're curious, this is what the final answer looks like. And the important thing to notice here is that this generates a unique solution because all these values are well defined. If we know xi's and yi's, then I can calculate all these things and it's only going to give me one possible answer. And so what that means is that we can program a computer to do these calculations for us. We don't have to do a lot of creative problem solving to find the m and the b. It just falls out of the equation, assuming the assumptions of our situation are in place. All right. And so that's why calculators and spreadsheets and so forth are able to do this calculation for us. Although the formulas aren't hard, if we had to do it by hand, we could, but for the most part, we'll be using a spreadsheet. So that's the introduction to linear regression. We'll see it in action in our next video. We'll see you there.